Okay, so let's review. Isobaric means same pressure, right? I wrote that really small. My apologies. Isobaric. Okay. Isometric. Same volume, yep. Isothermal. Same temp. So what does a isothermal process look like on this graph here? On this graph. Straight horizontal line, right? So just to have it, I'm just going to put it. So that line I just drew is isothermal. What about isometric? Vertical. Okay. So that would be isometric. Okay. You can have multiple processes, right? You can have going from one state to state 2, 2 to 3, 3 to 4, and depending on how things go, you could have an isobaric process, an isometric, or isothermal. Okay. There was one more. We'll cover this later, but it's polytropic. This is PV raised to the n is a constant, and we're going to cover that next chapter. The n is only raised to the v, correct? Is that what you said? I'm pretty sure that's what I thought I heard. So on the TV graph, that's a constant pressure, right? Okay. If I were to do PV that's how constant temperature lines look like. Okay. Isobaric would be a horizontal line across. Okay. And these are all the F locations. These are the VG locations. This line on the left, or the left side, is compressed liquid. The middle section is a mixture, and I'm going to make sure you understand. Over here, it's either a superheat, a vapor, or a gas. Okay. This left line is called saturated liquid line. So this left purple line that I'm drawing right here, saturated liquid line. The brown one, saturated vapor. Now, quality is only the left of the line to the right of the line. Anytime you're to the left, you don't put anything for quality. Anything to the right, you're all vapor. Quality is actually still 1, but you don't put anything. So I noticed that in the homework, some people found the quality. I didn't mark off. If I did, I'll give you that point back. But we don't put anything for quality if you're a superheat or a vapor or gas. Okay. Now, do these bottom ones? I'm going to continue using this. Thank you. Do they always have to be VF or VG? No, but always remember that saturated liquid are all subscript with F, all on the right side subscript G. Okay, good. What, say I'm right here, and I call this, say this is at state 2. What do I need to know at that point to find our volume or enthalpy or whatever? Quality, yes. Quality is this X symbol, okay? So you have to know quality. How do you find it? Well, there's an equation in your book that shows you how to find it. You would need a VF, VG, and you would have to know either specific volume, those 3, or you can do F, HF, HG, or H, right? You have to know those 3. Actually, I can give you the equation. Use your cheat sheet. Remember the cheat sheet. Everyone kind of forgets about that. So this would be the equation to find your specific volume anywhere. If you're on the left, the compressed liquid side, use tables to find values. Always assume the subscript F. Okay, that'll give you close enough. If you're a mixture, you have to go to the tables to find your VF and VG. Okay, so these have to be found on the table. And what is VFG? That is VG minus VF. Okay, so remember that. I saw some students forgetting about that. If you are a superheat or a gas or a vapor, you can use tables, or you can use the equations that I'm going to talk about here in a second, which we talked about last class. Okay. Any general questions on this? If you notice, I've been repeating this every class, because if you know where everything is, this can help decipher like any type of problems that you're dealing with in the homework or the test. Okay. All right, so let's just go through ideal gas, and then we'll get to some practice problems. So we'll do these practice problems, and then Friday. All right, so ideal gas, and then we'll write non-ideal. Well, we'll do the one on the left first. I don't even think I need it. So there is a random assortment of equations, right? Well, they're not really random. They're all the same. Just one more. So you have P equals rho RT, PV equals MRT, PV equals RT, PV equals NM RUT, and then the red are the criteria that's valid to use those ideal gas equations. Okay, so both of them have to be satisfied to use those black equations. If one fails, then you go over to the non-ideal, and you just add this Z to the right side. So all of these, just you have to add that Z. Bless you. It's contagious. So if it's a non-ideal, that just means it doesn't compress a certain way. Okay? This Z can be, usually it's less than 1. And the Z is a function of your TR and PR, and that's where you have to use a graph. Okay, or that chart that I showed you. All right, let me just show you that real quick right now, then I'll come back here. Here, I'll put it over there. What's that?
You got a lot of subscriptions on it.
Yes, we do. You have a question about them?
Just NM and RM.
Yep.
What are they?
NM is the number of moles, so the M is moles, okay? And then RU is your universal gas constant. which is like 8.3.
Well, that's okay.
Yeah, that's RU, yes. Yep. Yep. Yep, keep asking. Week 6, no, where was this? That might have been here. So I'll just go through this and I'll get back to that. So here you have Z on your y-axis. You have your PR on your x-axis. And each one of those lines represents, I keep forgetting to use this, different TR values. Okay? So you just have to figure out what your TR is. If this is 2, then you'd use that one. And then remember your PR. Okay? So if we go back to this, TC and PC are found in your table. Those are your critical points on the TV graph or the PV graph. Okay? So temperature. Let's see, what else we got? We got pressure. So let's do degrees C, kilopascal, volume, and then phase change or phase description. So we got -4, 10, 320, 0.0065. We got 850, 600, 90. Some more saturated vapor. And what are we dealing with? We're dealing with R-134A, so refrigerant. So these problems, yeah, they're 4 parts. They're not a word problem, but when you get to a word problem and you're at either a temperature or a pressure or a specific volume, you can use these methods in these problems to figure out where you are in the vapor dump. Okay? So right now, the easiest one that I would do is C, because we already know that's saturated vapor. We're on the line, on the right. We already know what VG would be and all that. So I'll wait a few more minutes or a minute to make sure you've got these numbers. Or does everyone have these? Looks like everyone may have these. Okay. So let's do C first. And I'll make that a little bigger. And again, I like to do TV. You can do PV. You can do whatever you want. We know we are saturated vapor. We're here. So we're VG. So we know the pressure is 850 kilopascals. We know that V is VG. And what else do we know? Ah, yes. Temperature is Tsat. The pressure is also what? PSAT. Okay? Because we're on the line, we're in the middle, that's during a phase change. And that's what they are. Yes. Yes. Good. I didn't even think of that. But yeah, the quality is 1. Yep. So let me write these numbers and we'll go to the table. 0.024 meters cubed per kilogram. This temperature is 33.45 degrees C. Okay. Questions? Actually, no, we want to go to the chart, right? So it should be right here. So it's refrigerant, SI. Oh, did I do SI? Yes, okay, good. They're SI in the test. So refrigerant, I think, is A11. Yes, right here. And we're dealing with pressures, right? Not temperatures. And it was 850. Get that zoom right in there. So we're here. Oh, that's too far down. So 850 is right here. Okay. Zoom in some more. The second column over is your temperatures. Then we have, what are those? Next column over. That would be VF and then VG. Yep. Now they don't give you VFG, but they give you HFG. Okay? They just do that because we'll talk about later why they give you HFG. Okay? But they don't, remember, they don't do that. Questions? All right, which one do you want to do next? No matter? Want to start with A then?
Yeah, sure.
Okay. All right, so A, temperature is minus 4 degrees C. P is 320 kilopascals. And tell me one method of what we need to do.
You can just use the pressure chart.
Yep, to find what? Yeah, so use your pressure of 320 and figure out your TSAT and compare T to TSAT. Or use your temperature and find PSAT and compare P to PSAT. Okay?
When we have to interpolate for either one.
No, I think they're both in there.
I think, yeah.
I think they're, well, I would find, so say the temperature was maybe 3, but you know the pressure is 320. Find the one that's perfectly or close enough in your table. Okay? Yep. So I think I found TSAT. So TSAT at 320 is that right? 2.46 degrees C. Let's find out. So 320. Yep, look at that. 2.46 degrees C. That's why they use refrigerant in. And we'll talk more about that later on too. Okay, so that means that TSAT is greater than T, right? So we're dealing with negatives and positives. So we are a compressed liquid. Somewhere over here. So V equals VF, or close enough. Oh, I also noticed I would write out the full numbers that the tables give you. Those are accurate. They have instruments that measure, I mean, otherwise they would have rounded, okay? Just because they have that correct, okay? Boom, done with A. Questions? Okay, let's do B. Is it making sense more now? And yeah, I know there's word problems. There's going to be word problems, but if you identify the type of process you have, that's why I reviewed before processes, you can then figure out where you are at each state. Okay, if you're in the middle, you better find what? Quality. Okay, just remember that. Okay, part B, temperature, 10 degrees C, and we know our volume. What does this mean?
We can use our 10 degrees C to check for our volumes and see where that relates to the VG and VF.
Correct. Yep. Yep. So let's compare VF and VG. And this is just for my notes for you if you come back. So 10 degrees C. So we got to use these tables, right? So the third column over, third and fourth, okay, so I want to zoom right in. So 0.0, is there 2 zeros? Yep, did I write 2 zeros? Yeah, okay, I thought there was 3 zeros, okay. So at 10 degrees, this is VF, so there's 3 zeros. And then this is only 1 0, so we have to be, just as a quick reference, we're in between. We're a mixture. And so we are a mixture, so we're in here somewhere. So go ahead and write that equation I gave you before. So V equals VF plus the quality VFG. Oh, was it asking to find quality? No. Okay. But you could, right? Okay. All right. What do we need to know, though? Pressure. Yes. The pressure is PSAT at 10 degrees C. And that pressure, you're probably all wondering what I was doing, huh? A little bit? You should have just said, hey, what are you doing? And the temperature is also what? TSAT. Yep. Now, just always remember that this black line is a constant pressure. That's only if the pressure through each process is the same. Okay? So if the process changes and it's no longer a constant pressure, then this point might drop or might come up. Okay? So you just remember that. It's not always going to be the same. The reason why this is the same is because it's a constant process for pressure. Okay? If the pressure changes or something else changes, your states could line up this way. So just be careful on that. All right? Does that make sense? All right. And why don't we just check that? Yep. So 414, right? Good. And we got one left. We did see, so let's do part D. Temperature is 90 degrees C. Pressure is 600 kilopascals. I found PSAT at 90 degrees C, which is 3,247 kilopascals. Since PSAT is greater than P, we're superheat. This pressure is 0.6 megapascal. So let me give you this number, and we'll look at the chart. 0.0463 meters cubed per kilogram. So this is, we're going to use table A-13. Let's go to the superheat tables, which should look like grids, right? Mm-hmm. And we need to find our pressure, which is 0.6, And Joe's not here, but this is sometimes, this temperature right here is that temperature, okay? Then these are then the temperatures. Those are, they're not saying they're saturation temperatures on the left, okay? So right here, and our temperature was 90. So this whole row across, and boom, that's our volume right there. I hope that's what I wrote down. Yep. Okay. So later on, next chapter and the chapter after, we're going to use the same process, but we're going to have to find H, because that's a combination of your internal energy and your flow work, which we write in the first law. And so you can then find, this H's are used to find the power of a turbine. Okay, so we'll get there eventually. So we have ammonia. I'm going to make a sketch for you. It's in a piston cylinder device. So we have ammonia. It's a saturated vapor initially. So hopefully that's a ring and a bell. So let's make this nice sketch over here. Saturated vapor, right? On the line, yep. It undergoes an isothermal process in which the volume doubles. So we want to find the initial pressures, not temperatures. So P1 and P2. And little v1 and little v2. Okay, so that's what the word problem read. It's ammonia, initially 0 degrees, saturated vapor. Then it says it goes from 1 to 2. It's an isothermal process, and we want to figure out P1 and P2, V1 and V2. First thing is always remember, if I wanted to find, we don't need this right now because it didn't give you this, but if I want to find the pressure inside there, what do I have to show? Free body diagram on this piston. Okay, so you have weight, you have P times A, you have P atmosphere times A. Okay, then write Newton's second law. Okay, forces are balanced. The pressures don't add up and balance. It's the forces that are balanced. Okay, so always remember that. I noticed that in the homework when I passed back, so make sure you fix that in your homework if you messed it up. So here's the problem. What do we need to do? Pretty much I wrote the keywords down over here, right? This is state 1 right here. So we'll put a subscript 1 here, and I'll relabel that V just to make my space. So I'm going to zoom out just a tad. I'm going to start the solution here just so there's space. You should start it below if you want. Tell me what V1 is equal to. VG. Yep. At what temperature? 0 degrees. .2892 meters per kilogram. What is P1? Saturation pressure, PSAT. At what degrees? 0. This becomes 429.6 kilopascal. If you notice, everything that we did in the previous problem is applied to the word problem. You just have to figure out, okay, we're dealing with ammonia, we're dealing with a saturated vapor, okay. This was a test question, they didn't have, you don't have ammonia in the back of your book, right? So I actually gave them the charts. So not only did they have to read they had to kind of look at a new chart and decipher that. But that was part of the lifelong learning that I was trying to get to the students, okay, for our ABET accreditation thing. So, okay. What about state 2? So the volume doubles. So that's easy to find, right? I should have made a heading, right? -5. State 1. State 2. V2 is 2 times V1. That's easy enough. 0.5784 meters cubed per kilogram. Okay. Now what? Are you stuck? Shouldn't be. What's the temperature?
0.
Yes. Why? It's isothermal. We know it's a perfect horizontal line. Holy crap, where are we? Superheat. So how do you, where do you got to go find the pressure?
Superheat.
Superheat tables. Now you could have used equations, right?
Yeah.
So P2 could be equal to RT over little v, right? You rearrange that equation. People could have done that. It would have been fine. But I think I told them to use superheat, the tables. And when you do this, you roughly get, because there was interpolation, about 200 kilopascals. But if you did use the equation, where would you find R? Table. I think it's appendix A1. Okay. What does the temperature need to be in? Kelvin. Yes, you had to convert it to Kelvin. Yep. I don't think I have any stats on this, but that took students probably a half hour to do when I did this. Then they had another ideal gas one. So does that make sense what we did here?
Yeah.
So you got to look at the processes and identify what's going on. Yes, Deb?
It does make sense. I was just, so I guess I was just confused. You said, so how would we find P2?
You just go to superheat tables, and what you need to do is you have to know your temperature. So let me show you here. So here's the superheated tables, right? So what you need to do is, say we're at 40. I'll use this. Say we're at 40 for temperature. You have to go to every block where you have V and figure out, okay, is that value for V what we had? If it doesn't, go to the next one for V. You have to keep going throughout all these different pressures to figure out where you are. Once that one matches, that's your pressure. Okay? That make sense? Everybody? Or actually, one of the homework problems, I think you had to do that. So, yep. Okay, other questions?